Hello everyone, today we will cover evaluation metrics that are used in machine learning techniques. So, we have already seen different types of machine learning techniques that can be used in different types of problems like regression, classification or clustering. In each and every case generally we have different evaluation metrics. So, using these evaluation metrics we check the goodness of results of your machine learning algorithm or technique that you are applying for a particular problem. So, let us start. When we are evaluating the prediction of machine learning techniques, so generally for given data instance x, the function that we are learning is hx and the value that will be predicted is y hat. So, the actual value may be y corresponding to x and we are learning this function or relationship between y and x, and we are trying to learn this relationship in terms of function, and then we are trying to find out what is the evaluation of machine learning techniques in the sense how much correct this function has been learned. So, we can say y is the actual value, and if these two values are different, in that case there is some error, and we can measure this error. There are so many methods, one of them is absolute error. So, in case of absolute error we can say this absolute error for a single training example will be when we will take difference of hx and y, where hx is the value that is predicted by the machine learning technique and y is the actual dependent variable value. So, when we will take mod of difference of this, we will get the absolute error for that particular instance x. In the same way, if we have more than one instances or multiple training examples, so in that case absolute error will find out mod of this difference for each training example and then we will take average of this. There is another method to find or define measure of this error. So, that is sum of squares error. So, in case of sum of squares error we do not take just mod of hx minus y, but we take the square of difference of actual and predicted value, and then we take sum over all the examples and then we multiply it by 1 by n. So, in this way we get the average sum of squares of error. So, these absolute or sum of squares error are especially useful when we talk about the regression problem, because in regression we know the values that we are predicting are continuous values, and if the predicted value is different from the actual value, so that difference is the error, and then we have seen either the absolute error or sum of squares of error. So, we can find out any of these errors in case of regression problem, while in case of classification problem where your prediction is not a numerical value, it is a label. So, in that case we can define error as a number of misclassifications. So, mathematically we can define it as 1 by n summation of delta hx y, where y is the actual label of the given instance x, hx is the predicted label of that instance x, and then delta of hx y is a function that can have one of these two values, either 0 or 1, and if delta hx y is 0, it means both predicted value as well as the actual label both are same, and delta hx y is 1 if these values are different, and then we can take summation over all the instances, and to find the average we will multiply it by 1 by n. Confusion matrix is very famous in machine learning, and this can be used as a evaluation technique, particularly in case of classification. So, if this is a binary classification problem, then we will have 2 cross 2 matrix. If it is a 3 class classification problem, then the confusion matrix that we will get as a result will be 3 cross 3 matrix, and if it is a 4 class classification problem, the confusion matrix will be 4 cross 4 matrix. So, in this way we can say that depending on the number of labels in our problem, in our classification problem, you will get the size of the confusion matrix. So, we will see the example of binary classification. So, in case of binary classification, we can assume one class is the positive class and another class is negative class, and then in the matrix there are 2 columns. One column is corresponding to actually positive number of instances that are there in the data set, and in the same way actually negative instances that are in our data set. And as a row we can again say there are 2 rows. One is corresponding to predicted positive, means the instances that are predicted as a positive instance by the used machine learning technique, and predicted negative means the instances, number of instances that are predicted as negative by the machine learning algorithm. So, now we can say in this 2 by 2 matrix there will be 4 entries. One entry will be corresponding to predicted positive and actually positive. So, this entry is called as true positives, means these instances were actually positive and the machine learning algorithm also predicted them as positive, and that is why these are called as true positives. Then we can talk about the second entry, that is corresponding to predicted positive and actually negative. So, these number of instances or these instances corresponding to these entries are those instances that are actually negative, but the machine learning algorithm predicted these instances as positive. So, it means here this is the case of misclassification. The actual level was negative, but the predicted level is positive, while in the previous case it was the correct classification because the actual level was positive and the predicted level was also positive. Now, we can talk about the third entry, that is corresponding to predicted negative and actually positive. So, this is again misclassification because these are corresponding to instances that are actually positive. So, these instances levels are positive, but machine learning algorithms predicted the level of these instances as negative. So, it means there is misclassification, and these are called as false negatives because these were actually positive, but falsely machine learning algorithm predicted it as negative. And then the fourth entry, that is corresponding to actually negative and predicted negative. So, again this is the correct classification case. So, all the instances that represent this entry, this fourth entry, these are correctly predicted, and these instances were negative, or we can say the level of these instances were negative, and your machine learning algorithm also predicted the negative level for these instances. So that is why these instances are called as true negatives. So now as a result, when we talk about confusion matrix, so we will get a metric where we will have 4 values. These 4 values will be in these different entries. So if we are having some value in the first entry, that is true positives, and suppose that value is 95, in that case we will say that 95 instances are true positive instances. It means these instances were actually positive and the machine learning algorithm also predicted them as positive. In the same way, if we have suppose 5 number in the second entry of this confusion matrix, in that case we will say that there are 5 false positive instances. It means there were actually these 5 instances were actually negative, but machine learning algorithms falsely predicted them positive, and that is why these instances are called as false positives. And in the same way, suppose there are 10 instances that are in the third entry, and in that case we will say that these 10 instances are false negatives, because these instances were actually positive, but the machine learning algorithm predicted them as negative, and that is why these instances are called as falsely predicted as negative, and that is why false negatives. In the same way, in the fourth entry, if we have suppose 100 instances, or this fourth entry is having the value 100, it means there are 100 instances that are true negatives. It means these 100 instances were actually negative, and machine learning algorithm also predicted them as a negative, and that is why these are called as true negatives. So this is very important concept in machine learning, what is confusion matrix, and then what are the meaning of these 4 entries: true positive, false negative and true negative, that are different entries of this confusion matrix. So if we can get confusion matrix as a output of any classification algorithm, we can easily find out what is the accuracy or what is the goodness of results of this algorithm, because from this algorithm we can directly find out the number of true positives, number of false positives, number of false negatives and number of true negatives. Now based on this confusion matrix, many evaluation metrics have been defined. So first of them is accuracy. So accuracy is nothing but the correctly classified examples in the data set. So this we can find out by summing true positives and true negatives, and then we can divide it by all these 4 entries. So in this way we will get the accuracy of the machine learning algorithm. So we can say that accuracy is true positives plus true negatives upon true positives plus false positives plus false negatives plus true negatives. There is another evaluation matrix, that is precision. So precision is defined as the accuracy of positive predictions. So we are only concentrating on positive instances, and then we are trying to find out what is the accuracy of the positive predictions in this particular case. So this can be defined as true positives upon true positives plus false positives. So we are talking about only positive instances. So out of these positive instances, few instances may be true predicted as positive, and few of these instances will be predicted as negative instances. So, if positive instances are predicted as positive, these are called as true positives, and if positive instances are predicted as negative, this is the case of false positive, and that is why accuracy of positive prediction can be defined as number of true positives upon number of true positives plus number of false positives. So, this is a trivial way to have perfect precision, and in this case to make one single positive prediction and ensure it is a correct precision. So, 1 by 1 will be 100%. The next evaluation matrix is recall, or it is also called as sensitivity, or it is nothing but true positive rate. So, true positive rate, we can say that it is a ratio or a proportion of positive instances that are correctly predicted by the classifiers. So, we are talking about all the positive instances that are predicted by the classifier, and what is the proportion of these positive instances that are correctly predicted. So, this is true positive upon true positive plus false negative. So, false negative means these were positive instances, but these are falsely predicted as negative. So, actually these were positive instances, and that is why in the denominator we are having all positive instances from the data set. So, that is true positive plus false negative, and then we are trying to find out ratio of positive instances that are correctly predicted. So, it means in the numerator we must have only true positive. So, true positive rate or recall or sensitivity is defined as true positive upon true positive plus false negative, or simply we can say that true positive upon total positive instances in the data set. Then the next evaluation metric is specificity, or it is also called as true negative rate. This metric gives us the ratio or proportion of true negatives that are correctly predicted by the model. So, here we are talking about all the negative instances, and then out of all these negative instances, what are the negative instances that are correctly predicted. So, this metric formula will be true negative upon true negative plus false positive. So, false positive means these were actually negative, but falsely these instances are predicted as positive, and that is why false positive. So, we can say that it is true negative upon all the negative instances. So, that is why Tn upon n. And the next evaluation metric is false positive rate. So, false positive rate is ratio or proportion of actual negative cases that are incorrectly predicted as a positive cases by the classifier. So, these are actual negative cases. So, it means on the denominator we are talking about all the negative instances, but we are talking about this false positive rate is giving us the actual negative cases that are incorrectly predicted as positive. So, in the numerator we are having falsely predicted as a positive. So, that is why false positive upon false positive plus true negative. So, in the denominator we are having all the negative instances, and in the numerator we are having out of these negative instances those negative instances that are falsely predicted as a positive instance. So, this is false positive rate. So, these all of these evaluation metrics can be easily calculated if we have confusion metric, because all these metrics are defined by few of these entries of confusion metrics. So, true positive, false positive, false negative and true negatives. Only few of these entries will be are being used in the formula of these evaluation metrics. So, these are very famous evaluation metrics that we use in case of classification problem. There is another evaluation metric that is called as F1 score. F1 score is the metric that combines precision and recall, and this is nothing but the harmonic mean of precision and recall. So, it favors the classifiers that have similar precision and recall. And there is one question that why we are taking harmonic mean here, why not regular mean. So, in case of regular mean, what happens when we are taking mean, we are treating all values equally, and in case of harmonic mean, we can say that more weightage is given to the low values. So, here we can we want to check whether one of these precision or recall is very high or very low, and that is why in this case it is better to take harmonic mean of precision and recall, and that is why F1 score is defined as a harmonic mean of these two metrics, precision and recall, and that is why the formula for F1 score is 2 upon 1 upon precision plus 1 upon recall, and then we can simplify it and get the final expression. And there is a precision recall trade-off. We can't get the perfect value for both of them. If precision is high, in that case recall may be low, and vice versa. So, it is not possible that we can improve both of them. So, many times we do not want also that both precision and recall is high. So, in some cases we may be more interested in precision, in other cases maybe we are more interested in recall. We will see the example where precision may be more important, and the other example where recall may be more important. For example, if we talk about classifier that detect videos that are safe to our kids. So, in this case we can say that we want very high precision, because this will not leave any porn video, or it will not detect, it will not classify any porn video as a safe video if precision is high. And in this case, if recall is low, it is okay, but precision must be high. While if we talk about classifier that detects the shoplifters on surveillance images, in that case this is the just opposite case. So, here classifier with low precision. So, where your security guard will get a few false alerts, that will be okay, but high recall, so that almost all the shoplifters will get caught. So, in this case we will need high recall, and low precision will be okay in this particular case. So, we have seen the example where one of these metric or precision is more important, while in the other example recall is more important, and unfortunately we can't have the best value for both of these. So, if we want to increase precision, recall will automatically reduce, and if we want to improve recall, then precision will be reduced. So, we will always need to find balance between these two, and depending on the problem, as we have seen, there may be problems where precision may be more important or recall may be more important. So, based on those problems, we will need to find out balance between these two metrics. So, in the next class, we will see some curves that are based on these evaluation metrics that we have seen in today's class. So, I am stopping here, and we will see the ROC curve and AUC in the next class. Thank you.